All right, so we're going to talk about specific methods for a while. The first one we're going to talk about is gravimetric methods. What do you think of when you hear gravimetric?
Um, Gravity?
Very good. So we're measuring the mass, and gravimetric methods are all about analytical methods in which the signal is the mass or a change of mass. This type of method is a direct analysis because the analyte is the species that is weighed. So that's nice. And remember, we talked a long time ago about how if you can get an analysis to be related to a change in mass, then that's a good thing because our scales are pretty good at being stable. All right, so an example is trying to identify how much lead ion there is by precipitating out something that's solid, taking it, weighing it, drying it well, weighing it, trying to remove any other materials that aren't interacting with the lead oxide or whatever it is you're measuring, and then finding out how much mass there is of it. Now, if you take a sample and you perform a chemical reaction in which there's a change, or you're measuring a solution before and after in terms of mass, then we can call that an indirect analysis because we determine the analyte using a signal that's proportional to its disappearance or its removal. Okay? All right. So a precipitation, gravimetry method is one in which, again, something like, in this case, we have mercury chloride precipitating, and the concentration of mercury chloride that precipitates is going to relate to the mercury ion. Okay? In gravimetry, we deposit the analyte onto an electrode, and then we measure the mass of the electrode. So have you heard of electroplating material, like taking spoons and making them look silver or gold, something like that? Gold plating,
Yeah, I've heard of that.
right? When you do that, if you have a mass or a balance that can measure that small change in mass, then you can find out how much was deposited. And this is pretty safe generally because the electrodeposition will continue until there's nothing left to deposit. Okay, volatilization. What do you think that might mean?
Evaporate off something?
Very good. Volatilization is where we evaporate something that's volatile, and so you can look at the change in mass that way. Particulate. We determine the analyte by separating it from the sample's matrix using filtration of an extraction. Okay. So, conservation of mass, you know that the equations, any chemical equation, the amount of lead ion here has to relate directly to the mass of the lead oxide in this case. We're not going to be losing any mass along the way. You always have the same, the conservation of mass. However, that's as long as you don't accidentally toss some of the material in your cleaning steps or in your rinsing steps, for example. Okay. So let's talk about precipitation gravimetry. This is probably relatively familiar to us because a lot of the problems where we talked about solubility dealt with, 105, 106, dealt with forming solids, precipitates, metathesis reactions in which we get a solid, right? And the relative concentration of chloride ion changes the concentration of silver ion in solution as follows, right? As you add chloride ion, right, the concentration of the silver ion decreases. But then look what happens if you begin to add too much chloride ion. What is this saying is happening as you add more and more chloride ion?
Oh, it looks like the chloride ion starts to form, what do you call those?
complex ions?
Yeah, complex ions.
Very good. Complex ions, which will allow some of the chloride, so silver chloride, to remain soluble and also form these other types of complex ions. So the concentration of your silver ion will not always get down to our zero, so we won't be able to get it all. But in general, the amount that we get is significant enough to make a prediction of the concentration of chloride ion, or silver ion, sorry. Now here is another graph that shows us the concentration of calcium fluoride as we add F minus in solution, right? So this one clearly reaches a minimum, and in some reactions this is the case. And so this is nice because the amount of the calcium fluoride that you have in solution will relate to the fluoride ion concentration and to the pH, because here we're changing the pH, right, by adding HF to give us our fluoride ion concentration. And this, again, we did this back in 106 where we predicted at what pHs certain metals would be insoluble, right? And we predicted at what pHs we could use to separate, for example, mercury, what was it, lead or mercury, or lead or silver, lead or silver. Okay, so maybe we should do a practice problem like that to remind ourselves. So here I have some KSPs for lead, or silver hydroxide and lead hydroxide. Okay, now we talked about ladder diagrams a little bit before, but what's interesting about this KSP is it relates to, like, if you think of this silver ion, this compound here dissociating into silver ions and hydroxide ion, right? Then the amount of hydroxide ion is basically going to be related to the pH of the solution, right? Because the pH is related to the hydrogen ion concentration, and the hydrogen ion concentration is related to the hydroxide ion concentration. So we get this similar type of dissociation, lead 2 ions and 2 hydroxide ions, for the dissociation here of our lead 2 hydroxide. All right, and we can then calculate at what hydroxide ion concentration, and thus hydrogen ion concentration, this silver hydroxide solution will form. So, for example, the KSP for this reaction, right, the KSP here equals the silver ion concentration times the hydroxide ion concentration, and that equals 2 times 10 to the minus 8. So if I have, I can solve for this because that's x squared equals 2 times 10 to the minus 8. So I can just take the square root of 2 times 10 to the minus 8. Okay, so 1.41 times 10 to the minus 4. The hydroxide ion concentration equals 1.41 times 10 to the minus 4. Okay, so I take that value, I'll take the negative log of it. What does it do if I take the negative log of it?
That's the POH?
That's right. And then what?
14 minus that.
Okay, 14 minus that gives us the what?
The pH.
That's right, 10.15. So our pH here is 10.15. And now, if the concentration of the hydroxide ion is less than this, there won't be enough hydroxide ion to precipitate out silver, and so this will the silver ion will be soluble in solution. Okay, so 10.5 or any pH that is higher, and the silver hydroxide will not form. So you have your silver ion in solution, and you can add hydroxide ion until the pH equals 10.15. Once the pH equals 10.15, silver hydroxide will precipitate out. But before then, the silver hydroxide will remain in solution, or the silver ion will remain in solution. Okay, we can do the same thing for the lead ion here. This one, however, is going to be our x, and this is 2x here. And this one is squared, right? Because hopefully you remember, well, let's write it out for us. Lead ion, hydroxide ion squared, right? And 2x is the concentration of the hydroxide ion, so we can put that in there. So we got 4x squared times x, that's cubed. That's set equal to 1.43 times 10 to the minus 20. So 1.43 times 10 to the minus 20 divided by 4, and then we take the cube root of it. All right, and so I get 1.53 times 10 to the minus 7. What is that?
That's our hydroxide ion concentration.
Very good. So how do we get our pH?
Negative log. And then 14 minus.
Very good. So 7.184. So which one is more sensitive to the hydroxide ion concentration?
Well, the KSP 1.43 times 10 minus 20 is much smaller, so it must be the lead, right?
That's right. And we also see at 7.814 the relative concentration of hydroxide ion in water. I mean, if this is your relative hydroxide concentration, it's much lower than the hydroxide ion concentration there. So this says that if I take a solution of silver ion and lead ion, whatever their counter ions are, nitrate, acetate, they're going to have to be soluble with lead and silver, obviously. And then I raise the pH to 7.2, right? I should effectively remove all of my lead from solution, but my silver ion should still remain in solution. You see that?
Okay, yeah, interesting.
So when you're performing a gravimetric analysis, you're causing a precipitate to form. And remember, a precipitate is going to generally be something like a three-dimensional lattice, like this crystal of silver chloride that we have here. And as the three-dimensional lattice comes together, the silver ions and the chloride ions come together, and again, they're not soluble because the silver ion is just too small for water molecules to satisfy the charge that it has. And so the chloride ions and silver ions, they're very similar in size. They form a very close, they have a very large lattice energy, right? So you can get, however, inclusions, right? You can get occlusions, which is basically ions trapped within the growing precipitate. Inclusion, which is randomly dispersed, but the occlusion can actually be an ion that's trying to coordinate with the cation, right, or anion. And so we perform a digestion, and hopefully the idea of a digestion is we slow the process down in which we precipitate our solid. And slowing it down then allows for these the crystals that we form to kind of be in equilibrium, to slowly form, unform as it's mixing, and then slowly form again, trying to allow the occlusions and inclusions to be expelled gradually. All right, you can get stuff that's gradually absorbed to the surface. Digestion can help this as well, but sometimes you'll always there's always a chance that you get something absorbed to your surface, or something that what we call co-precipitates. And this is basically the same thing. The absorbent is an example of a co-precipitate. As your material precipitates, something else precipitates on the outside. Okay. You can control the particle size of precipitant if you slow the rate of the precipitation, or the particular growth rate. All right. And here's an example of a silver chloride, right? A silver chloride precipitate. If these two come together and they can't form a larger piece, right? We say that they aren't coagulating. So coagulation is smaller pieces coming together to form larger pieces, okay? This coagulation can occur more effectively if there is fewer amount of absorbent on the outside. And so you can also use a concentration of ions. In this case, we are using, for example, the nitrate ion or sodium ions give a secondary absorption layer with a negative charge that balances the primary absorption layer. And this solution outside the secondary absorption layer remains electrically neutral. Therefore, coagulation cannot occur if the secondary absorption layer is too thick, because the individual silver chloride particles are unable to attach to each other close enough. And this can be a problem if these particles are too small for your filtration method. Okay, so when we want to filter the precipitate, there are some things that we have to take into account. We want to make sure the filter, the pore size is correct. We also want to make sure the size of the filter paper itself fits in the funnel, right? Because filter paper is hygroscopic, right, it's going to be absorbing the water, just like any piece of paper would. We're going to need to kind of either dry our filter paper really well, or we can even use a process called ignition that will convert the paper to carbon dioxide and water. So basically we're going to heat it up high enough temperature that it burns away, completely burns away. You have to have very good paper for this specific. Poor quality paper will leave behind inorganic ash. So you have paper that's good for ignition, right? And if you're going to perform this, and also you have to make sure you have enough space and oxygen flow to allow the ignition to come to completion. All right, so look at this here. This is our round filter paper. We fold it up into quarters like this, and then from this we can make a little cone shape that will fit into our funnel. When we're adding our supernatant to the funnel to get extra precipitant, right, we can use a glass stir rod like so. This will prevent spillage coming down the side here. And then there's also scenarios where we use a filtration device that has an aspirator connected to it. So we pull a vacuum on, first we pull it on a trap, and the idea here is if this water fills up, we don't want it going into the vacuum and ruining the vacuum. So you include a trap, and you pour your sample here, and right in here there is a piece of filter paper there. You can also do this without a piece of filter paper and have a crucible here that you measure the mass of the crucible before and after